Hi students, good morning to all. Today we are discussing connected components and spanning tree. The third topic of third unit, first part. Okay, the connected components, these are all applications. These are all applications of depth first search tree. Okay, here if you have an unidirected graph or directed graph, uni in the sense only single directed way. Okay, coming to the what is a unidirected graph in the sense we are taking some connected components and articulation points and bridges and by connected components. Coming to the directed graph, we have to be studied here cyclic or acyclic graph. And coming to the one more topological sort, in the sense topological in the sense structure of a network, and we are say strongly connected graph components, strongly connected graph components. Here these are the particular applications of depth first search, unidirected graph or directed graph. Unidirected graph, if we have connected components, articulation points, bridges and biconnected components. And coming to the section of directed graphs, we have studied about cyclic or acyclic graph and topological sort. Topological in the sense structure of a network and strongly connected graph components. First of all, if you have to learn about what is a connected component, now we have see the definition of exactly connected a component. An undirected graph, here you look at the diagram here, this is the undirected graph, is called a connected graph if there is a path in the sense way, if there is a path between any two vertices and this direction and that direction, go front and go back direction, it is nothing but a connected graph. What am I said to be exactly connected graph? An undirected graph is said to be a connected graph if there is a path between any two vertices. This diagram represented undirected graph. And coming to the definition of a connected component, what does it mean exactly? We have studied here a connected component in the sense it is a subgraph. What ma? It is a subgraph in which any two vertices are connected. Okay, listen carefully. In which two vertices are connected to each other by paths. What I meant to say here, it is a connected component is also a subgraph in which any if you have two vertices are connected to each other by the path, so which is connected and which is connected to no additional vertices. Okay, which is connected to no additional vertices of the supergraph. One more name of supergraph is nothing but a main graph. Here look at the examples of connected component. Here we have to look at one vertex to another vertex in which any two vertices are connected to each other by a path and which is connected to no additional vertices of the supergraph. This is the examples of a connected component. Look at this diagrams: 2 to 3 connection, 3 to 4, 2 to 4, 4 to 5, 3 to 5. The connection will be there in which any two vertices are connected to each other by paths. Coming to the algorithm for connected components. Now what you have to say here, algorithm for connected component. Now we have to study about step by step a process to solve a particular task by using this connected component algorithm. If we have to be solve the connected component a graph, let us I will take the name connected component G in the sense, let us if we have to be taken G in the sense a graph G. First step, for each vertex V belongs to G dot V in the sense V in the sense vertex, it belongs to graph of any vertex, it belongs to graph of any vertex. And the second step, make a hyphen set of V if we have to make a set of vertex. And coming to the step 3, for each edge U comma E belongs to G dot E. U in the sense here unvisited vertex, V in the sense visited vertex. Here unvisited vertex and visited vertex, it belongs to a graph of edges. Okay, and coming to the fourth step, if find hyphen set, if you want to find a set of unvisited vertex, it doesn't equal to the find hyphen set of v, in the sense visited vertex. If you want to find hyphen set of u, it's not equal to find hyphen set of v. U in the sense unvisited vertex, v in the sense visited vertex. Okay, and coming to the fifth step, we will need to union of u comma v. Union in the sense combine. What you can say, combine unvisited vertex and visited vertex, and we have to be taken here same component unvisited vertex and visited vertex. The first step here, if you want to find set of u, it is equal to find set of v. In the sense here, if you want to find set of u is equal to find set of v. And coming to the second one, if you want to be written true, yes, this find set of u unvisited vertex is equal to the find set of visited vertex, then it returns 2. Otherwise else it returns false. Okay, this is the concept of connected component. And coming to the spanning tree, already we discussed in second unit the greedy method, first part, minimum cost spanning tree. Before we are discussing minimum cost spanning tree, first of all, if you want to be learn what is a spanning tree. Yes, exactly what is a spanning tree. Now let us listen carefully, otherwise you can't able to understand what I am saying these points to you. Okay, coming to the spanning tree. Spanning tree is a subset of a graph G. Graph G will consist of number of vertices and number of edges. Okay, it consists of vertices and edges. Simply we can say, let us take a graph G, A to B, B to C. Now if you want to draw to be a spanning tree is a subset of graph G. Already I mentioned the definition to you. Okay, here look at this subset. Spanning tree is a subset of graph G, in the sense you don't want to form a loop. A to B, B to C, connection will be there. And coming to the one more diagram here, A to C, C to B. This is also a spanning tree. What does it mean exactly? A spanning tree is a subset of graph G which has all vertices. Listen carefully, Amma. Which has all vertices are covered with minimum possible number of edges. Okay, with minimum possible number of edges. Hence, we can say a spanning tree does not have a cycle. Hence, a spanning tree does not have a cycle, and it cannot be disconnected. Listen carefully. Spanning tree is a subset of graph G which has all vertices are covered with the minimum possible number of edges. Hence, a spanning tree does not form a loop or cycle. Okay, and it cannot be disconnected. Let us I have to be taken a graph G, A to B, B to C, C to A. Let us I will take a graph G, simple example. Now I have to be converted it to a spanning tree. Now A to C is there, C to B connection will be there, A to B connection will be there, B to C connection will be there, and A to B, A to C connection will be there. This is nothing but which has all vertices are covered with the minimum possible number of edges. Now we have to be look at what is the weight of a spanning tree. Okay, weight of spanning tree, we indicate that W of T, weight of spanning tree, W of T is the sum of weights of all edges. We have to be calculated here the sum of weights of all edges in a spanning tree. Okay, A to B I have to be given the edge with the minimum possible weight 1. A to C I have the minimum possible weight 2. Now I have to be added the sum of weights of all edges in spanning tree T. 1 plus 2, how much? 3. So the minimum spanning tree is a spanning tree with the smallest possible weight. With the smallest possible weight we have to be studied here weighted graph G. Let us I consider these a weighted graph. Here I will take some notes, 4 notes. Let us consider 1, 3, 2, 4, 6, 5. I will give some minimum smallest possible weights. Okay, the sum of weights of all edges in a tree. Okay, now the minimum spanning tree from weighted graph. This is the spanning tree. Now we have to form. Don't form to the loops. Already I said you. Okay, which has all vertices or covered with minimum possible number of edges. Hence, a spanning tree does not form a cycle. Yes, exactly. Now we have to be look at here. 1 3 2, there is no cycle here. If we have to be added the sum of weights of all edges in tree, 1 plus 2 plus 3, that will be assigned to 6. Okay amma. What the real time examples of minimum cost spanning tree? It can be used in design of networks. In coming to the, if we have to design of networks, minimum cost spanning tree, it can be used in design of networks. Mainly it is based on least cost path. Mainly it is based on least cost path with no cycles. Okay, mainly it will based on least cost path with no cycles. Okay, and coming to the second key point of main real time example, coming to the airline routes, minimum cost spanning tree, if you need to find their airline routes, vertices represents like cities and edges represents route between cities. Okay, already if we have discussed at second unit spanning tree, but I have to repeat once again. Okay amma, if you have any doubts regarding the topic of connected components and spanning tree, here in this concept of spanning tree, first of all, if you have to learn mainly what is an articulation point. What is an articulation point? In according to graph theory, a biconnected component is a maximal biconnected subgraph. Already I say here, listen carefully. A biconnected component, it is a maximal biconnected subgraph. Here any connected graph decomposes into a tree of biconnected components. Let us take any connected graph. We need to decompose into a tree of biconnected components called block hyphen cut tree of the graph. Whatever it may be, if you have to say cut tree of the graph, block cut tree of the graph. So here the blocks are attached to each other. The blocks are attached to each other yet shared vertices called cut vertices of articulation point, called cut vertices of articulation point. Simply articulation point in the sense any connected graph decomposes into a tree of biconnected components called block cut tree of the graph. So the blocks are attached to each other yet shared vertices called, we can say, cut vertices of articulation point. Okay, this is the concept of connected components and spanning tree. Thank you ma, one and all.